This is just a map of the public agencies within our GSA. We have Lagoon Irrigation District, Riverdale Irrigation District, Liberty Water District, Stinson Water District, Clark's Fork Reclamation District, Layton, Riverdale, and Lanier. That is all the public agencies that are within our GSA. Most of this area, again, is covered by mutual water companies, and then portions of it are covered by Fresno County and the non-districted lands. This is a contour map of groundwater elevations. So usually twice a year, the depth of water is measured at various wells. And by knowing the elevation of the well, that information can be converted to elevation of the groundwater. Just like if you had water on a hillside, put it on, it would run to the low side of the hillside. Groundwater does the same thing. It runs to the lower elevation. So this is higher elevation up in here, which is Consolidated Irrigation District. And the water flows underground perpendicular to these contour lines. So these little arrows here indicate how that groundwater flows perpendicular to these lines. So you can see the groundwater flows into us, across us, and flows out on both ends. This is what's called a cone of depression, so that's a low area. Water is flowing into this area. This is the McMullen GSA, which does not have any surface water rights. And so water is tending to flow into these areas that have no surface water because of the groundwater extractions. This map just shows an idea of how many wells we have and where the wells are concentrated. This information is coming from the Department of Water Resources and Fresno County well records, which we know are incomplete, but it's the information, again, it's the best information we have. And so this is a compilation of irrigation and domestic wells. And so you can see the darker colors here as it goes to blues and purples are higher concentration of wells. And so most of the concentration of the wells are just around Highway 41 through this area. And as you get west, not as many wells. We did do a water quality review as part of the GSP. The majority of that information came from the GAMMA program, which is the Groundwater Ambient Monitoring and Assessment Program. And what this program does is it looks at community water systems and tests the water in those systems periodically. There were, I believe, 73 wells that we evaluated and collected the information on within our GSA and around the buffer of our GSA. And just a summary of that information. What we did was we looked at the data in what we refer to as 3 different zones. So a shallow zone being 0 to 150 feet, the intermediate being 150 feet down to what's referred to as the E clay, which we'll explain in just a minute. And then the deep zone is below the E clay. These chemicals all had some exceedances of the health advisory levels in the zones where they're indicated. So in arsenic, somewhere within that range of 73 wells that were evaluated, there were arsenic hits above the limit within the shallow zone, the intermediate zone, and the deep zone. So some of these constituents, it's not in every zone. Some of them it is. A lot of these are naturally occurring. And so it's something that we have to monitor. And what's required as Sigma is that we can't make the water quality any worse with the management actions that occur with groundwater. We are not charged with improving the water quality, but we cannot make the water quality any worse as a result of groundwater pumping or activities that are implemented by the GSA in response to Sigma. So what we have in the plan, and we'll show you a few here tonight. One way to evaluate water quality is with what's called a box and whisker plot. It's a little hard to see, but in the middle of this box, or somewhere in this box, there's an X, which is the average or the mean value that was observed for that constituent. The box itself represents the lower and the upper quartile of the results. So you have a series of data, and you look at the average, and that gives you your X. You look at the top, or exclude the top 25%, exclude the lowest 25%, and that gives you your box, essentially. And then the whiskers are going up to the extremes, both the upper and lower extremes. And occasionally there's a data point that just doesn't make any sense. It doesn't fit with the rest of the data, and that's called an outlier point. And so it's shown, but it's not included in the averages or in the box itself. So the queries that we ran on this water quality were focused on identifying the highest reported concentration of each constituent for the most recent 10-year period across all zones. We actually looked at data all the way back to 1989, but we focused on the most recent 10-year period. So here are some box and whisker diagrams for various chemicals of concern, constituents of concern. So arsenic, again, average is the X. The box represents where most of the values are occurring, and then the whisker is kind of more the extremes. Arsenic is one that the regulation was changed probably 10 years ago or so, where it went from 50 parts per billion down to 10. When it was at 50, we wouldn't have had any concerns. When they basically dropped it to 10, now we have exceedances pretty much all over the board. You can see that it kind of bounces around, but it stays, kind of in this range on average of 20 or so. Chromium, no real concern. The MCL is the maximum contaminant level. So it's up here, we're running down at this level. Chromium's not really much of a concern. Fluoride, bumping up against it, maybe a couple data points above it. Gross alpha, a few times it's above it. On average, it's maybe right at it. So gross alpha is one we need to keep an eye on. Arsenic's definitely one we need to keep an eye on. But what you'll notice on these graphs, as our water level has been declining, we're not observing trends that indicate any real increases as water level is decreasing. So during the drought from 2012 through 16, our water levels declined pretty significantly, but these constituents did not correspondingly indicate that. It's kind of bouncing around on some of these. We're not seeing any direct rise, at least on average, any direct rise related to decline in groundwater storage, which is a positive thing, but it's something that we have to keep an eye on it and move forward. A few other ones here. Lead, that was an odd measurement or point in 1 year. The rest of them are all low. Ones like this are suspect, to be honest, and so it's things that we have to keep an eye on. If we had a hit like this, we would want to check it again and see if there's any kind of trend with it. Trends is really what we need to be evaluating. Because of the fluctuations that we're seeing, we have to look at what's happening and see if there's any correlation with trends as the water levels change. Nitrate kind of bounces around, has some data points high, but for the most part, it's not a concern. TCP had 2 points in a couple wells that are actually just at the edge of our GSA area, and uranium again is kind of bouncing around. So these are all constituents that we're going to be keeping an eye on as we move forward with the water quality. One of the other things that we look at in the basin setting is just what are the soil conditions like in this GSA. This is just a map from the Natural Resource Conservation Service, and it just gives an indication of soils, green being coarse soils or sandier soils, moving through as it goes into more of the yellows and then the reds, higher percolation rates down to very slow percolation rates. Again, we're sitting here in the North Fork Kings. This is Central Kings GSA, which is Consolidated Irrigation District again. You can see the river's coming through here. Coming off the river, a lot of good recharge areas potentially through here. Consolidated Irrigation District's had a recharge program for 100 years. Those soils extend into our GSA some, but as we get out to the west side, at least on the surface, the soils are not as conducive for recharge. There are some opportunities to do some things with recharge if you get below that surface soil a little bit, but it's a little more involved than if you're just putting a basin in. You mentioned the E-clay. So the E-clay is also called the Corcoran clay. It's probably more commonly known as the Corcoran clay. Years ago, the clays were mapped underground, and they were given letters, A, B, C, D, E, F. The primary ones are A, C, and E. And the E is the Corcoran, again, Corcoran clay. So the USGS, the Geological Service, has mapped the extents of these clays based on well logs. And you can see, again, this boundary is our GSA. This purple line is the A clay, so that's a shallower clay. It's at about 50 to 60 feet generally. The C clay comes up in this area. It doesn't connect here because they didn't have enough information to connect it, essentially. Doesn't mean it's not there somewhere, but we don't know if it continues up or if it closes off or what it does exactly. But that C clay sits at around 250 feet or so. And then the Corcoran clay has been mapped in a couple of different locations, either across here on this kind of this mustard color line or the darker line. This darker line is what probably the more recent mapping of it indicates, and that's what's included in some of the modeling that's done by the state. What this indicates is that this area here is probably a thinner clay layer, and so it's not as confining, but it's an area that we have to be concerned about. So these clays, what it does is you have these A clay, the C clay, and the Corcoran, and water moves underneath it, and you have either confined or unconfined groundwater zones. So again, that's what makes this area complicated. This is a map of subsidence that's occurring in our area. This is mapping done by NASA and provided by the Department of Water Resources. This darker area here indicates between May of 2015 and April of 2017 that we had between 10 and 15 inches of subsidence. So that's definitely an area we have to be concerned about and watching subsidence. At this point, we haven't seen any significant impacts of that subsidence, but it's something we have to keep an eye on. And just on water budgets, we'll wrap up with water budgets in this session. What a water budget does is it summarizes water use, and we use it to estimate the amount of groundwater pumping. Simply, basically, the water demand that's not met by surface water or precipitation has to come from groundwater. Those are our sources of water. The water supply within the Kings, the surface water supply within our North Fork area is almost exclusively from the King River, but we do have areas that do not have surface water supplies. So there's a number of what are called inputs and outputs on these water sources, and when you look at the difference between those two, that's the change in groundwater storage. But we know there's some errors in or lack of confidence in some of those components, and so that adds to the uncertainty for a water budget. And these are all the components that factor into a water budget, so we came up with numbers for each of these. But a simplified version is basically you have water flowing in either on the surface or underground, you have precipitation, you have evaporation, evapotranspiration by crops and people use, you have surface water flowing out, groundwater flowing out, and then you have changes within the groundwater system, which are recharge as well as pumping. So we had to do this for a historical period, a current, and a future period. And our current overdraft is estimated to be on average about 63,000 acre feet per year. Looking into the future, we had to factor in climate change, and so looking at potential impacts on ET rates and precipitation. And our future overdraft would be almost 69,000 acre feet per year because of those climate changes, estimated climate change, if our water supply and cropping pattern remain constant. But we have identified projects and management actions that reduce that 68,000 down to zero, because again, we have to be sustainable in 2040.